Hi guys, welcome back to Data Every Day. Today we're looking at a data set of cars in an auction in US. And we have a bunch of data about each car, and we also have a price that the vehicle is going for in the auction. So we're going to try to predict the price based on the other features. And we're going to use a whole bunch of different models for that. And I guess we'll see which does the best. I'm importing NumPy and Pandas just for working with the data. I don't think we're actually going to use this today, but we are using the train test split function and standard scalar from sklearn for pre-processing, and then all of our models. So let's go ahead and import that, and I'm going to load in the data using pandas.readcsv. And I can grab the file path over here, I'm going to copy it, paste it in, and take a look. So we have 2,500 rows and 13 columns, and you can see a good number of these are categorical. We can take a little closer look at the data with data.info. It's nice to see here that there are no missing values in any of the columns. We have a max number of non-nulls in each column. And you can see we do have 1, 2, 3, 4, 5, 6, 7, 8 object columns. Additionally, you can see we have at least one column here we're not going to need. And we also this looks like some sort of identification number. And these columns, maybe the lot also might have a really high number of unique values, so we might not need these columns either. So let's start pre-processing. So I'm going to make a function called preProcessInputs that's going to take in our data frame, and it's going to return the same data frame, but first let's make a copy of it. So this is sort of like we're making a copy of our data and then applying our pre-processing steps and returning the result. So we can call it x as the pre-processed version of our data. That will be pre-process inputs. I'm going to pass in data. Take a look at x. Right now it's exactly the same as data. But now we can apply different functions in here and see how it changes the result. So I think the first thing we might want to do, we know there's no missing values, so that's not a worry. We really want to focus on encoding these categorical features. So we can get a good amount of information about how to do that by looking at the kinds of values that are in each column. So we can make a dictionary that's going to map column name to a list of unique values in that column. So x sub column.unique, and then take it as a list, and that's going to be for every column in. And I don't want a list of all the numerical values, right? I really am only interested in the brand, model, title status, color, state, and country, and condition, I guess, which are the categorical or object columns because they're encoded as strings. Now the lot is also categorical, but I'm going to take a look at that separately. Actually, it might make more sense instead of doing the list right away. We just take the length, so we can see the number of missing values in each column. And I'll do that for all columns. So actually, x.columns. So this will map each column name to the number of unique values in that column. And this shows for the numerical columns as well, but it gives us a good sense of how we might want to go about encoding these columns. Now, you can see from most of these, they actually are nominal features, which means there's more than 2 values, and they don't take any specific order. The only one that might not be a nominal feature would be the title status. Maybe it's clean vehicle, dirty vehicle, or something, in which case we could... Well, actually, let's see. Yeah, there's only 2 values. So this can be encoded as a binary feature. Country as well could as well. So it looks like we're probably going to need nominal encoding or one-hot encoding and binary encoding. Now the condition column, this can be interpreted as an ordinal feature. So I think we might need all 3 encoding schemes today. So let's make those functions up here. We'll have our binary encode function. We'll have our ordinal encode function. And we'll have our one-hot encode function. Now all three of these functions are going to take in a data frame, and it's going to take in basically all the columns we want to encode, along with some other values. So for the binary encode, we want to pass in the positive values as well. For the ordinal encode, we want to pass in the orderings, and I'll explain more about this in just a moment. For the one-hot encode, we want to pass in the prefixes. And so in all three of these functions, we're going to start by creating a copy of the data frame, and at the end we're going to return the data frame after we've performed the transformations. So let's start with binary encode. For example, title status. Let's look at what values we have in there. So title status dot unique. This will show us all the values in there, and we can have clean vehicle or salvage insurance. Now I'm not sure exactly what this means. We can get a little more information here. This feature included binary classification. Okay, it's just saying that's a binary classification column. So not giving us too much information, but that's okay. Pretty much with binary columns, it doesn't really matter if there is an order between them, because you can always just encode it so that one of the values is 0 and the other is 1. And it's its own feature. You don't have to create multiple columns out of it. So how are we going to do that? Okay, we want to pass in the value that we want encoded as 1. And that's what we'll call the positive value. So I'm going to pass in basically a list of tuples that have columns and positive values. So for column, comma, positive value in this thing, columns with positive values, we're going to take the column, so df sub column, and we want to modify a copy of it by applying a lambda function to it that takes some x, which will be, for example, if we're doing the title status column, it's going to be a given one of these. And x is going to be sent to 1 if x is the positive value, and otherwise it'll be sent to 0. And this will effectively binary encode the column. So we specify which one we want as 1, and the other one just automatically goes to 0. And that's actually all we have to do for binary encode. That will do the whole thing. Ordinal encode is sort of similar, but this time we're going to pass in the columns with the orderings. So if we look at the condition column, down here, if I just look at the unique values in condition, okay, there's actually quite a bit of entries here. Okay, and this can be an issue. Now, if this guy wasn't showing up, we would be okay, because we can still order it. But there is an expired. Now, it's hard to say if it expires after a certain period of time or for some other reason. So it might actually be a good idea to nominal encode this, because we have this entry. Pretty much, you're not really missing out on too much information if you nominal encode. You know, it's sort of it's on a case-by-case basis. Sometimes a nominal encoding will provide more information. Sometimes a ordinal encoding will. But because we have this and it makes things a little complicated, I'm just going to nominal encode it. And that was our only potential ordinal column, so we're actually not going to need this function today. So we're just working with the one-hot encode for nominal columns. And so one-hot encode is basically, we're going to use Pandas.GetDummies to take, let's use this column as an example. We take a column and we get the dummies for it. And you can see each one of these unique values has been sent to its own column. And in that, for a given example, we have all zeros and a single 1, where the 1 represents the original value of that example. So if we look over here, example 0 had 10 days left as its condition. So over here, we have a 1 in the 10 days left column and zeros in all the others. So we're going to use these dummies to one-hot encode all of the nominal features. And I want to note that we can include a prefix here. Let's call it COND for condition. And that will just put COND at the beginning of every column name, so that when we create these dummies, we know where they're coming from. We can see the original column that they came from. Alright, so here we're passing in a list of tuples, pairing up columns with their prefixes. So for column and prefix in this guy, columns with prefixes, we're going to take, we're going to create some dummies to start. And that will just use the Pandas.GetDummies function that I just showed. And we're going to pass in df sub column. And we'll set the prefix equal to the prefix that we're passing in along with it. And then we're going to want to take those dummy columns and put them onto the end of the data frame. So for this, we're going to use pandas.concat for concatenation of data frames. And we're going to concatenate the original df and the new dummies side by side, so axis 1. And then we're going to drop the original column from which we created the dummies because we no longer need it. And that's it. That's all we have to do for one-hot encoding. And these are the only encoding schemes we're going to use. So now in our pre-process inputs, we can actually start doing that encoding. And there is one thing we should probably do before that, is remove this column. It's just unnecessary. df equals df.drop. It's just a duplicate index column. So it's called unnamed 0, and we're dropping from axis 1. So now if I run this and we get our x, and we take a look, no, not this, over here, you can see our unnamed column is gone. So here's all our data. Oh, actually I shouldn't have deleted that because there's actually some more information we want to get from it. Okay, so let's do the encoding. But I would like to point out these guys, VIN and lot. We have 2,499 examples, and you can see there's almost that number in both of these columns. So because these columns have such a high number of unique values, the percentage of that 2495 divided by 2499 is 99.8%. So 99.8% of the columns of the values in these columns are unique. So there's very little information in these columns. Because each one is separate from the others, with a few exceptions, there's very little overlap between the examples, and they don't provide a lot of comparative description about the examples, like relative to each other. So we're going to drop the VIN and lot columns along with unnamed 0. So let's put these in a list, and we're going to put in VIN and lot. And now if we run this and look at x, we no longer have those columns. And I believe all the rest here are valid and useful for predicting the price. So, alright, let's actually do the encoding now. So, drop unnecessary columns. And then we will binary encode. What columns are we binary encoding? There's only two. I believe it's title, status, and country, because there's two unique values in each of those. So binary encode the title, status, and country columns. So to do this, we're going to use our binary encode function, which takes in a data frame and the list of tuples with columns and positive values, and returns a data frame. So we're going to store it in df, and we're going to call binary encode and pass in df and columns with positive values, sort of a long name, but it's descriptive, is going to be a list of tuples that match a column name to a positive value. So the first column name we have is the title status. So title status is our column, and that's going to be passed in along with the positive value that we want. So there's two possible values in here. So if we look at the unique values again, let's see actually I mean, it doesn't really matter which we use, but I like to use the minority class, the one with many fewer examples, as the 1, because it's sort of like an anomalous occurrence. By default it's 0, and then we eventually have a 1 in there. So let's use salvage insurance as our 1, as our positive value. So I'm passing that in, Um, and then we are also going to binary encode the country column. And so this needs a positive value as well. Let's take a look at the country value counts. And so it looks like Canada is the minority class, so let's use that as a 1. And I'm passing that in here. And so this should perform it for us. Let's see that now. We're going to... Oh, binary encode is not defined. I never ran this block. Okay, there we go. And we'll take a look. And sure enough, we now have 0s and 1s in these columns. We can just double check that to see we now have... Uh-oh, that's not good. Apparently we have all 0s. Oh, this may be actually... If we look at data, there might be some white space here. If there's some white space, then essentially everything's going to go to 0 because the positive value we specified isn't found in the data. So this condition will never be met, and we'll never have any x's go to 1. So it's good that we checked that. We actually, to get a better sense of this, we can type .values. Oh no, that'll only give us .keys, I believe. Okay, here it is. You can see there is some white space before. So all we have to do is go in and put a little space there. And let's just check for title status as well, so that we know if there's white space. And no, there isn't. So now if we run this, let me take a look, and we get the value counts now. You can, oh, sorry, for x. All right, we have 0 and 1. And for country, we should also have 0 and 1. And sure enough, we do. So these have been successfully encoded. And now let's do the one-hot columns. So we're going to one-hot encode the, what is it, brand, model, color, state, and condition columns. And so to do this, again, we just have this function that takes in a data frame and a list of tuples containing the columns with their prefixes, and it's going to return a data frame in the end. So let's store it in df, one hot encode, pass in df, and columns with prefixes, which is going to look like a list that's matching up columns with their prefixes now. So the prefixes can be anything. It's just to uniquely identify these columns and indicate which columns they originally came from. So we're doing brand first, and we can just use like the first 2 letters maybe. So br. Oh, not a colon here, a comma. And we have model. Maybe md. I keep doing a colon. Hold on. All right. Then color. So we could do CL. State. ST. And last one is condition. And we can pass in the prefix CD. So now, if we run this, take a look, you'll see we now have all these one-hot columns. I can't see them all, but I have faith that they're all in there. And you can see that all of the data is now in numerical form. So we have actually successfully encoded all of the categorical information. And so now we're going to try to predict the price column with all the rest of the data. So let's actually split df into x and y, where y is what we're trying to predict, and x is the data we're using to predict it. So y will be df sub price, right? I'm going to make a copy of it. And then x will be everything except price. So we're going to drop price from df, axis 1 for column axis, and make a copy. So now let's return x and y and get that back here. So now x no longer has the price on it, and the price has been sent to its own variable y. And then, so this is like a vertical split. We split off the y from the x. Now let's perform a horizontal train test split. So this is going to split some percentage of the data into a train set and the rest of it into a test set. so that we can use the train set to train our models and the test set to evaluate them. So we'll use the train test split function from sklearn to do this. We'll take in an x and a y and specify a train size. So 70% is standard and it works well. And we'll include a random state because this function also shuffles the data for us, so it's very useful. We don't have to do it ourselves. And so including a random state will ensure that the shuffle and therefore the split are always made in the same way when we run this notebook. And that's going to return 4 different sets of the data. We have xtrain, xtest, ytrain, and ytest. And then we can return those as the result of this function, as the output. So let's get those back here. And then let's take a look at xtrain. So it's the same as x before, but we're only working with 70% of the data, and the other 30% is in xtest. So I guess the last thing to do now is scale the data. So currently all of the columns take on different ranges of values. So we have only zeros and ones in these one-hot columns, and then we have all the way up to 151,000 over here. So we want to sort of standardize the columns so that they all take on the same range of values. And there's a few ways to do this, but we're going to use a standard scaler, which will give each column a mean of 0 and a variance of 1. So scale x with a standard scaler. So let's create a scalar object, and this is the standard scaler from sklearn, which I imported earlier. We're going to fit it to the train set only, because we're only training, we're only fitting the model on the train set. So we're sort of working under this assumption that we only have the train set available to us at the time of training. Now I know we don't, we have the test set as well, but we artificially sort of created a test set. In practice, we may not have the test set available, so it's always best practice to only fit on the train set for the scaler as well. So let's actually apply the transformations now with scalar.transform. So we're transforming xtrain, and then we're going to store the scaled version of it back in xtrain after that. And we'll do the same thing for xtest. So these will be test. And these actually return NumPy arrays. You can see if I return this and I check xtrain, it's been scaled, but it's just a NumPy array. So let's turn it back into a data frame after. Pandas.dataframe. And I want to include the column names. And the column names will be x.columns. And let's do the same thing for the test set. Okay, now we can see it as a data frame. And you can see that all of the columns have been scaled so that the mean of each column is extremely close to 0 for all of these. And the variances are extremely close to 1. So there we go. You'll note that our y has been unscaled. It's still in its original form, which is the right thing to do. I mean, it wouldn't make sense to scale y also, because if you got new price data, you basically want to keep y in the unit that it originally was. So I guess we'll start training our models. So let's check ytrain just to be sure. There it is. And we will start training. So I'm going to train a bunch of models today. All of these. So I'll just paste this in because it just takes a while to write this out. The models we'll use are a standard linear regression, k-neighbors regressor using k-nearest neighbors algorithm, an MLP regressor, which is a neural network, linear support vector regressor. So this is a support vector machine using a linear kernel. Then we have support vector regressor nonlinear, so this is using a radial basis function kernel. Then decision tree, random forest, gradient boosting, XGBoost, light GBM, light gradient boosting machine. This is extreme gradient boosting, and cat boost. And I'm going to fit each one in a for loop. So we're going to iterate. This is a dictionary that maps a name to a model, and we're going to iterate through each model and name pair in models.items. So items will return the dictionary key value pairs as tuples. so that we can iterate like that. And for each model, I'm going to call model.fit on xtrain, ytrain. And afterwards, I can print out a little statement that says the model was trained, so name plus trained. All right, and let's see. Model is not defined. Oh, this should be models.items. Okay. All right, and it's training each one. All right. And oh, we have a problem. Light GBM error. Do not support special JSON characters in feature name. So this is an error that appears sometimes with using Light GBM. There's a quick fix for it. We can use regular expressions to remove characters it doesn't accept in the column names. So for that, we're going to use import regular expressions really quickly. RE for regular expressions. And then in here, after we do the encoding, but before we do the split, I'm just going to include a rename for the column names. And the columns will be renamed using a lambda function that maps x to regular expression.substitute, and it's going to substitute any of the following characters, which I guess it doesn't accept, with a empty space. So it's just deleting them, and we're going to apply that substitution to x. I just did a quick Google search to find this. Apparently this, so I'll say fixes light GBM error. Alright, so I think it removes spaces from our column names. I'm not sure if that's exactly what was causing the problem, but now if we train them, we shouldn't get the error anymore. And as soon as that finishes, I'm going to want to print out the results. So results. So that's all of them. They've all been trained. And I'm going to, for name, comma, model, just like we did up here in models.items. Let's print out the test accuracy for each one. So we're going to print out the name, followed by accuracy. No, sorry, it's not accuracy. We're dealing with an r-squared value here because it's a regression task. R-squared score. And we can display it to, I guess, 5 decimal places. And format it with model.score on xtest, ytest. So the .score function will evaluate on the test set, and we can see all the results. So the r-squared score can take, it generally takes a value between 0 and 1, where 1 is the best score it can get. It's a measure of how dispersed the data is from our fit. And you can see some of these are quite good. We have one of 0.67. I believe this is the highest of all of them, as in the CapBoost regressor. But some of them are absolutely atrocious. If it's really bad, if the fit is really bad, it can go into the negatives. So we have some negative values. And you can see that our standard linear regression model has an insanely negative value. So you can see that this is just completely failing to do the job. Although we are getting some good results, especially using some of these gradient boosting techniques. Random forest also performing very well, which is a bagging technique, which basically just trains a bunch of models in parallel and then averages the results. So I guess that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.